This webinar series will be hosted by author Dr. Joseph Jacobsen. It will be presented in 3 parts today. May 12th and June 2nd will follow at 2 p.m. Eastern Standard Time. Dr. Jacobsen is currently Professor of Business at Concordia University in Milwaukee. His latest book, Sustainable Business and Industry, is being adopted across the country as a textbook for graduate and undergraduate business and industry coursework alike. During this first session, Dr. Jacobsen will define big data and all its characteristics while taking a closer look at the availability of big data in facilities and external data that impacts facilities operations. We will also be giving away a copy of Dr. Jacobsen's book to a lucky attendee at the end of this session. All of you have to do as qualify is to attend the webinar and fill out the survey at the end. Thank you for attending. Now, I would like to hand it over to Dr. Jacobsen.
Well, hello. Hi, my name is Joe Jacobsen. Good morning, good afternoon, good evening, depending on where you are. Here in Central Time, United States, it's 1 o'clock. And we're going to take a look at several different aspects today of big data. And we're going to start out with some aspects related to the book. And we're also going to make available a file to you for free download on statistics. Everything a manager should know about statistics, which is an appendix in the book. And so stay tuned for that, and you'll be able to download that free appendix for your use when you're doing your analysis on big data. What happened pretty much recently with big data is that there's been a lot of attention paid to the use of data because of the avalanche of data that's available to folks, but that's just about the way it is. There's a lot of data available, but there's not a whole lot of ability to be able to use that data for actionable items when you're making decisions about improving your operations and reducing operating costs and ecological footprints at the same time. And so during these 3 sessions, we're going to define what is big data, and we're going to look at how big data has been managed throughout many years because scientists have been using big data for a long, long time. And the advent of a data that creeped into business is merely using solid scientific methodologies in order to examine that data and to make decisions just like scientists would in laboratories. And why is this important? Because it works. It's something that's been going on for a long time, but the business community, especially given the amount of expert systems that are out there in energy management and especially in maintenance management, who is here in the room with me, and the data that's available through a lot of these systems can be used to make good decisions and reduce operating costs, get more out of people, and also extend the life of pieces of equipment and operate much more efficiently than we ever have in the past. So I'm going to start out talking a little bit about myself and the book, and then we're going to jump into the session. My background, as Harry said, is in the academic community, but I wasn't always in the academic community. I started out operating about 220 buildings, so I'm no stranger to facilities operations and maintenance. I had a large staff in a large municipality, and those 200 buildings, 200-plus buildings had a lot of expert systems. So I've kind of garnered up a lot of expertise in how to display, how to report on, and how to make decisions about data. From there, I moved into the academic community, and I've been teaching for about 25 years in this space. But then I became a dean over at MATC, Milwaukee Area Technical College, where I worked in the Technical and Applied Science Division and started the very first Sustainable Facilities Operation degree in the country and the very first Energy Engineering Technology degree in the country. And so that was really an eye-opener in terms of how to get this information out to people to be able to make better decisions about their operations in a higher level of technical proficiency. From there, I moved over to Pittsburgh, where I started the Energy Innovation Center and the academic side of that organization, and then came back to Milwaukee, where now I'm a teacher, and I teach decision sciences, but mostly in the area of economics, econometrics, macroeconomics, and others, and I consult with Johnson Controls and other organizations. My book came out in 2011, and I'm going to briefly go through some of that here. This is a, supposed to move down. Well, it seems to be a little stuck right now, but the book consists of about 9 chapters and 3 appendix, of which many of the chapters are dedicated to facilities. Chapter 1 is making the case for social responsibility, environmental responsibility, and it pretty much oh, there we go. It covers the corporate level, and that is to be able to integrate sustainability into the mission, the vision, the objectives, the strategies, and in particular, we're going to talk about today the measures and the tactical things that an organization can do to align itself to become more sustainable, more efficient, and reduce its operating costs. How do you start a sustainability committee? How do you put together a climate action plan? How do you put together an energy reduction plan? Chapter 2 is about reporting, and that also includes some of the corporate aspects. Now, between these 2 chapters, I go into some detail about climate change. The most important element, I think, in between these 2 chapters is that I pretty much specify the definitive question that so many people ask about climate change, and that is, how long is it going to take for some catastrophic effects? Of course, we are feeling the effects right now. There's no denying that. But in terms of how long does it take to increase the surface temperature 1 degree Celsius, and what does that look like for the future and our trajectory in specific units of time? So this is a pretty important chapter, and it goes into some of the aspects of it where it's not just a linear system. There are sudden jumps in behavior rather than just simply increasing every year by a given rate. So this is what I would call the original big data. If you look at the science, you look at the history of the Earth, you have those in the ice cores, of course, and that's big data that's been around, obviously, a long time. Chapter 3 goes into ISO, so more about social responsibility. Chapter 4 about measuring some aspects of social and environmental responsibility. And then we go into return on investment. Which is really important in Chapter 5. Go into how long does it take to pay down the installation of specific technologies in terms of its reduction of energy use, water use, materials, efficiency, and staffing. And so Chapter 6 goes into a what I call FESUP. That's a Financial, Environmental, Social Unity Project, FESUP, and use the methodologies of Six Sigma, scientific methods, and lays out how to engage and organize a project of continuous improvement with using maintenance management software, with using energy management software, and how to improve the organization and make gains that can be reportable to your boss, to the CEOs and the CFOs within organizations, and demonstrate that a lot of the decisions that you make that do reduce energy use also can save a bundle of money for the organization. Chapter 7 is probably the most applicable to this specific seminar in that it's about sustainable commercial and industrial operations. It goes into LEED buildings, goes into starting an energy action plan, and it also specifies energy auditing and commissioning and some of the occupations surrounding how to reduce the footprint, how to better run a building and make it much more efficient, and also use some of that efficiency for marketing of the organization. Chapter 8 goes into lean, which is directly tied to sustainability, in that it's all about the reduction of waste. And then finally, Chapter 9 goes into economics. Now, what's important is Appendix A, and that's what we are here today to talk about. Appendix A is about analysis. It's about using statistical methods, both descriptive and inferential, to make decisions about what you can do in order to improve your performance of your building, improve the performance of your people, improve the performance of your equipment, and even predict what is going to take place in the future by using some of the data to do that. And so we're gonna move forward and engage in some of the aspects of big data. Of course, one of the reasons why we're here is that we're all interested in reducing our waste. We're all interested in having very little to no waste in our organizations. And one of the examples of that, I guess you could say from an energy point of view, is comparing, say, a power plant to distributed generation with combined heat and power, and the efficiency ratings of each of those propositions. We can reduce our waste by as much as 50% by moving to distributed generation, combined heat and power, by capturing that waste, which is heat. And so here we've got a slide that reflects some of the waste in the physical sense that we're up against. And we all want to do our part, and we all want to be as efficient as possible, and for obvious reasons. And so we're going to examine the aspects of big data and what really characterizes big data to start with. So these are some positive attributes that can be attained by way of big data. Reducing operating costs, occupant satisfaction, and more intelligent staff. The training that goes on is extremely important, of course. Project justification with the return on investment. Developing a capital budget based on the expiration lives of pieces of equipment and the forecasts of what you're going to need in the future to be more accurate about that. And then, of course, the environmental aspects, the positive outcomes of being more sustainable are critically important. So here we're looking at the biggest of the big data. It's going back about 950,000 years. We can see that the measures of normal variability in CO2, this is derived from the ice cores, not just one ice core, but the average of all the ice cores in the given areas that they're taken from. And you can see that it's well under 300 parts per million. But the problem is that now we're about 400 parts per million. We're penetrating through a ceiling that has really never been recorded before. The increase, of course, over time, going just back to the industrial age, is apparent. And so this is just a sample of data and some of the displays of quantitative information that can be used. This is also world population. As you can see, it's steadily increasing. And the latest UN report, which is not included on this slide, this is just a couple of months ago, is forecasting that the planet is going to have 12 billion people. The old forecast was about 9 billion, and then leveling off at 9 billion for a long, long time, and then maybe declining after that. But the latest update that the UN has published is up to 12 billion. The planet cannot possibly sustain 12 billion people, especially given that people are increasing their quality of life in the third world at the same time. And so we see a trajectory here that it's pretty bleak. And so without being more efficient in our operations and without being more conscientious about how we use resources, we're in for a literal world of hurt. And so we all need to do our part for that. But the good news is that we can do our part and save money at the same time. So big data, what is it? So large volume, and I'll go into a little detail about what that means. But large volume typically means sample size, right? And that is the one of the hallmarks of big data. That now, given Facebook and Google and the amount of data that's available through those sources in real time, also the availability of big data in all the systems that you find in facilities, it's just tremendous. Just tremendous. I've been working with energy management systems and maintenance management systems for years and years, and it's just amazing how much data you can get from these systems. You can get the gradient down to microseconds if you'd like to do that, if you've got the ability to store that much data. And you can collect history files going back to the beginning of the installation. So there's so much data available out there in almost everywhere you go. But the question is, what do you do with it, with all this data? How can you get a hold of it and make it manageable so that I can actually do something with it? High velocity, of course, is another characteristic. It's coming at you fast today. It's coming at you so fast, it's real time. We were just talking about high-frequency trading before we sat down for this webinar, and trading on the stock exchange at the speed of light is 186,000 miles per second. And you think about that, how fast these algorithms are responding to changes in condition. And this is what's going on in the real world. So it's fast. When we talk about real time, it's moving at you. It's changing in real time. So the ability to be able to write a good sequence of operations for a piece of equipment, to be able to respond to conditions that change in a space based on some signal in real time is mandatory. You really need to know how to do that. So high velocity is certainly a big part of it. And high variety. The variables are more complex now. You get data from all over, but how do you get it into shape so you can actually do something with it? There's many more variables than there ever have been before. If you look at a typical energy management system today, you might have 2,000 points on that system. That's 15 or up to 2,000 or more different variables coming at you, and they could be in seconds. They could be taking samples of some condition in seconds or minutes, or you can even get it less than that. And so you've got many more variables coming at you. Some of the data is incomplete. It's mixed. It's also very complicated. So being able to decipher, what to do with this stuff is pretty critical. So one thing I wanted to point out about science and big data is that big data, the availability of big data makes it pretty interesting for scientists. Scientists typically will collect data, and then they'll draw conclusions from that data or support for some hypothesis, right? And so that data is typically in the form of a sample. And a sample is a subset of the population of data. But as data gets bigger and bigger, it becomes closer and closer to population. And so if you've got population data, you can dispense with inferential statistics because it's fact. And so this really changes the face of science. And a lot of people don't like it because they've spent their life studying statistics and inferential statistics and be able to support some kind of hypothesis and make predictions about what's going on. But with big data, when you've got population data, you can use just descriptive statistics. Now, this isn't the case for everything, but this is the territory that we're moving in. When you think about all the cameras that are at intersections, and the Center for Disease Control is checking for outbreaks based on Google searches for cures for conditions of a flu, you can see that the whole arena of data has been changing, and that the availability of data is far more impactful today than it's ever been before, and we're getting closer and closer to knowing everything about everything, and that's a pretty broad statement. But these are some of the attributes of big data in terms of science. The p-values, that's inferential statistics, they can become less and less valuable because you don't need to know the probability of it not being true if you have all of data in front of you. And so I won't go into detail on each one of these. I do this in classes, of course, that talk about characteristics of inferential statistics and model building with data. But you can take a look at this, and if you have questions about this, be sure to get them to me. High velocity, of course, again, streaming data, right? I think we're all used to streaming data today. The proliferation of real-time web-based data, data acquisition systems that are working in real time. You really have to get on board. You have to learn about how these systems operate and how you can interpret these characteristics that are reflected in the actual data. Again, nonlinearity, right? Not all of these systems are just straight lines. They jump all over the place. So you've got nonlinear systems as well. Incomplete data. Some statistical packages will automatically fill in the data for you. If you've got missing pieces, and it'll fill it in with the average, it'll fill it in with data in front or in back of that particular point. And so there's tools available to you that can help you when you're working with distributions of data and making decisions about that data. And we'll talk about the different packages that are available in statistics as well. So we look at kind of this is my version of the organization. It's a lot different than what you find in, say, a business program or something that describes the organization. I look at it from more the resource point of view. So all of these points can be served up in real time. And in many organizations, they are served up in real time. And so we've got natural capital, of course, which is the natural resources that are available to any organization in terms of what it's using. And this is all documented with data. And then we've got the human capital and the training that goes on with that capital, like we're doing today. And then we've got organizational capital and the methodologies of continuous improvement, which we're also addressing today. And then we have manufactured capital, the physical plant, the pieces of equipment, all of what makes up the assets of that organization, the fixed assets of that organization. And then, of course, behind all of that is energy. So facility operators are a big part of this. Facility managers and facility operators are the ones who actually manage and operate these facilities that deliver all of this within these walls we call a building, a facility. And so being able to decipher how to extract the information from these systems and integrate them is such a valuable commodity. And if you know how to do this, you can get a job anywhere. You can bring your organization to great heights because you'll be one step away from all the rest and one step above. So this is kind of my version of that. So these slides, of course, will be available to you through the Eagle website. And so we can take some of this data and we can start coming up with some ratios of continuous improvement for our projects based on the data that we've collected. You know, BTU per product, BTU per person, BTU per degree day, watts per square foot, watts per product, water, a water footprint. You can think of all of these different measures and ratios that you can use to watch and see if you're heading in the right direction or not. See how much you're improving. If you're making a wrong turn, it'll tell you, and you know you need to go the other way. So some of these ratios are pretty important, and it's important to measure the right thing when you're reporting. Obviously, when you're reporting out on electrical performance, watts per square foot is for lighting, and you need to use that. You can't use watts for the entire building. So you have to drill down into something that makes sense for the user, and for especially the people who are making the decisions about this. BTU per degree day. You know, if you are just a commercial facility without manufacturing, you'd want to measure your offset of that degree day in terms of BTU from the boilers and chillers, right? So you have to drill down, what's that boiler doing, what's that chiller doing, and then you have, you know, KW per ton. And so you have to measure the right thing at the right time and be able to report out on that, and then it will be accurate. It'll be accurate in what that performance measure is over time as you continuously improve. You know, for example, if you're measuring BTU per square foot, but you're in a big manufacturing plant that swings widely on its orders, it won't make any sense. It won't make any sense at all, because you may use a lot of energy at times of big order and little energy at times of small orders. And so you have to drill down, and this means that many times you'll have to sub-meter. And what do you do with that meter? You collect the data from that meter. And so you have to integrate that meter into your system and be able to develop some type of performance measure for that, and then get on top of that and figure out ways to reduce that performance, that usage. And so we've got some other externals, right? We've got utility performance structures. Obviously, that's becoming more and more a part of what facilities are going to be working with in the future. There's going to be two-way communications, not just one-way communication. In the past, you just use, but now there's going to be information going back to the utility. And obviously, it's going to be an extension of peak demand charges. There's going to be more and more of this as we move in the future. It's called smart grid. Smart grid systems that not only speak to the customer, but speak to the pieces of equipment, and the equipment speaks to the utilities. And we're going to see this unfolding in a big way. Industry standards. You know, how do you stack up against your industry standard? Do you belong to ASHRAE? Do you belong to the Energy Engineers Association? Do you belong to some of these associations that have these benchmarks for the standardization of performance for a specific type of key performance indicator that you're using in facilities? And are you higher or are you lower? And why are you lower? What are other people doing? What are those best practices that they're engaged in that can get you to the point at which you're performing at par, and then figuring out how you can be a leader and actually get ahead of it? And that's what I like to do. I like to get ahead and actually lead the charge rather than just stay in the middle, right? Of course, weather is a big deal, as you know, in facilities, and being able to set yourself up for that in terms of your, if you're locking in or hedging prices based on futures with natural gas and commodities, that's a part of the facility operations today. It wasn't too long ago, but today a smart and intelligent facility person is going to be engaged in that type of futures, and so those types of futures. Technological development, demographics, politics, suppliers, and think of all of them as opportunities to engage in some type of continuous improvement. This might be your power plant, so you can see in a mechanical space the amount of data that comes from a mechanical space. There may be 1,000 or 2,000, 3,000 sensors in this space, all spewing out data. And so being able to set that up, make decisions, and especially when it comes to maintenance, right? When you're getting a signal that the discharge temperature for a chiller is above 55 degrees, what's going to happen at that point? Or are you just going to let it go until it turns into a hot complaint? So you have to get in there, and you have to set yourself up a work order, and have that work order go to someone as a text message or an email or some type of signal, and get in there and take care of that problem before your customer ever knows anything about it. And that's the beauty of it. And so you never have a complaint. you need to get in there and write up these kinds of sequences so that you can respond to faults before they turn into some type of negative impact on your department, on your division, on building operations in this case. As you can see, these systems are pretty sophisticated. This is a real render. This is not a rendering, I'm sorry. This is a real mechanical space I worked with not too long ago. And again, data just spewing out and being able to maintain, operate, and control and troubleshoot these kinds of pieces of equipment. They're boilers, pumps, compressors, chillers, air handlers, and extending their life and making them run as efficient as possible by looking at the data, the sensors. What is the rate of change for some type of degradation curve? That is one of the best examples of usage of big data I can think of, where you're using elements of calculus to be able to predict what's going to happen with this piece of equipment and take care of that before it turns into a fault. This is the beauty of big data, especially in facilities. It goes in other places too. I can name out probably 50 different industries that use this same concept, but for different kinds of operations. And so you need to know yours. And this is, we're talking facilities engineering, plant operations, facilities management, building operations, just so much data available. And the price of these systems is coming down. That is the big difference too. So we're able to get at some of those. So what are some of these systems with all of this data running out? Well, take a look at this. If you don't know about data and you're going into even a halfway sophisticated building, you better understand quickly what's going on. You've got to get on board. There's no quite. Look at the systems that we have here. Access control and all the implications of access control, energy management systems, computerized maintenance, asset management system, camera systems, fire life utility systems, smart meters, expert systems, elevators, on and on and on. All of these systems are coming at you, and all of them have thousands and thousands of pieces of data. Wow. You really have to either get on board or get out of the way, because it's coming at you pretty quick, and it's not going to recede. It's going to get more and more and more sophisticated as we move forward, and as the price of these technologies come down and the integration of these systems becomes more and more accessible, it's going to get that much more complicated. So you really need to understand data. So this is just kind of one example of what's going on in facilities today, and this is not unreasonable. This is normal. I remember walking into the Sears Tower, just as one which is now no longer the Sears Tower. But I asked the operator. The operator asked me, pick a place, pick a face, and pick a time, and I didn't know what he was talking about. And I said, and I finally caught on. I said, well, how about 9 o'clock main entrance? And then all of a sudden he zoomed in. It was 9 o'clock main entrance on the screen, and I picked a face, and he zoomed in on that face and then printed it out for me. And a building containing probably 25,000 people. So you can see the sophistication that's going on with big data. The Willis Towers, I'm sorry. And so there's a movement going on. And so I'm really happy to be here today to be able to share some of this with you. And we're gonna spend some time on this over the next this session and the next 2 sessions on things we can actually do, get down to more specifics. So measure, right? Descriptive distributions, actual behavior of systems, of benchmarking to industry standards, testing for significant differences before and after you try a different technology. That's kind of my favorite. When I implement some kind of technology, I want to test and see if it's actually working. I'm not going to take a sales representative's word for it. I can't do that. I have to, the next day, go in and see, is this a significant difference from the day before in terms of performance of that system. If I got a heat recovery unit that I'm putting on this boiler, you better believe I'm going to be testing that unit the day that it's installed, and then comparing that to before the unit was installed. And this could happen for 1,000 different pieces of equipment. So this is just one way which science enters into building operations, because in the scientific community, let's look at medicine. These are clinical trials. It's the same thing. These are clinical trials, and you can do this right in your building operations and show. And then when you report out on it, you can bet your bottom dollar that you're reporting the truth. And so rational correlations, regression of building models, we'll talk about that later. And then display, right? Displaying figures and tables and reports and presentations, because we all got to report to somebody. And if you're a building operator and you're getting tapped on the shoulder because this organization wants to start a sustainability initiative, and they got to tap you on the shoulder because you're the most important you're the most important person in the building when it comes to sustainability, because you got your finger on the meter and all the equipment, well, you're going to have to produce. How are we doing? You know, that's going to be the question. How are we doing? And how are we doing after we change this? And what kind of projects would you propose to improve our performance? So these are critically important questions. So the data will help you to move down that path. So measure, 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 right? This is the key to performance. If you don't know how you're doing in terms of measurement, you don't know if you're doing worse. So this is seems pretty obvious, but you'd be surprised how many people enter into a project and then they never go back and measure how they're doing after it's done. If you're responsible, you're going to do that. So descriptives, right? The totals, the averages, the frequencies, the minimums, the maximums, you know, run charts and histograms, the ranges of some of these behaviors. So this is all pretty simple stuff that you can look at a distribution by dumping your data into an Excel spreadsheet and creating a chart that would give this kind of output. And so this is pretty much the introduction for this part of the conference. I'm going to move forward with a couple of other things. This is a chart I had, in fact, before we used energy management systems. I'm getting up in my years, I hate to admit, but even before energy management systems were available, I used to record data on this kind of grid, and I'd go downstairs and read the meter every morning at 6 o'clock to see how we were doing over the past 24-hour period, and then I would use that data in order to set different types of controllers on the boiler to see if we were using more or less, and I'd measure that per degree day for a commercial building. And that is pretty much the beginning of how to improve your operations. It's a very primitive way to do it, because you can write all this stuff in systems today and algorithms, and it'll take care of itself. You can watch it as a dashboard, and that's usually the way it's done today. But it really comes back to this fundamental idea that if you measure the right thing and you can get that information and you can look at it over time, you'll be able to tell how you're doing. And so if I was setting some type of controller higher or lower, and I saw that performance moving in the opposite direction, say I turned up the aquastat, for example, something as simple as that, and then turned it down, I would be able to find the optimum set point for that aquastat based on my BTU per degree day calculations for each day over a given month. And then I would set it right there. And then I'd recheck it every once in a while to see if it was still in check. Well, you can see how sophisticated this data is, but when it comes down to it, it's really not. What's going on in the background are some of these basic calculations that you can do with a piece of paper and a pencil. So, smart systems, right? We're gonna talk more about this, but you can see that the potential to reduce energy use by up to 50%. And I already mentioned some technologies you're going to see more of, like distributed generation with combined heat and power in facilities. We're going to see more distributed systems. We're going to see more microgrid kinds of systems. And there's a good reason for that. Power plants are typically about 35% efficient. I'll go through this and then we'll close it up for this event. But power plants are about 35% efficient at most. We also know that we can distribute that process, the power plant, at the facility and get up to about 90% efficient. So you think about that. You think that power plants, all that heat going up the stack, and that we have transmission and distribution losses, and then we have also we have the amount of energy it takes to get that energy to the power plant, especially if you're using coal, and you're down to way less than 35% efficiency rating. And so we're going to see more and more of this, of cutting back on the amount of waste that is part of the energy supply chain. And as we do that, sensors and data is going to become more and more a part of everyday life. And I've already given you, all of those different systems that you can find in a building. And so it's not a future thing. It's happening right now, and we all have to get on board with that. But also in the future, I'm giving you some evidence that it's going to become more so as we move forward. We're going to see more and more data.
Joe, we have a question that came in from the audience, and I think now would be a good time to take it. The question is, now that ISO 5001 energy management has been approved, how do you see it complement the other ISO standards as it is about energy information or management?
Well, yeah, the 5,000, I'm sorry, it's 50,001.
I'm sorry, 50,000.
Yeah. 5001 ISO also complements 14,001. I mean, 14,001 is actually was widely accepted as the environmental performance standard and certification for facilities around the world. 50,001 is starting to emerge as specific to the energy portion of that. And so they fit hand in glove. They really do. And so if you're working with ISO 14,000 to get your facility certified in that area through somebody like the American Society for Quality or some of the other organizations that train for that and audit for that, you would also benefit from using 50,001 to capture a second area at the same time and verify that in fact you are at this performance level. I prefer 50,001, and maybe, I don't know if I should say this or not, but LEED, of course, is one of the most widely used standards for facilities performance in the U.S., U.S. Green Buildings Council, of course. But 50,001 really gets down into more about the energy performance of the facility. It's far more technical, and so I see them as working hand in hand, as complementing one another. So you can do all three, I would say. And it offers a wealth of training for the folks who are working in the facilities. You take some of these standards and the training that goes along with it, and it really does prepare you to perform and then conduct the audit to make sure that you are performing up to that level. So I hope that helps a little bit, but yeah, I see it really complementing 14,001. I'm most familiar with 14 because it's been around for such a long time. I've been in Asia, in Europe, and South America, all over, and I'll see the 14,001 certification all over the place. So 50,001 is starting to take off.
Joe, we have another question that came in. The person asked, well, my facility is only about 15,000 square feet. I heard that ASHRAE is established a standard, or is trying to, that we need an energy manager in our facility. Am I too small to worry about energy management?
Oh, Well, I'll respond to that first by saying nobody's too small to worry about energy management, because I worry about energy management and I live in an apartment. But actually, no. 15,000 square feet is, yeah, it's a small building, obviously, very small. You're talking about the size of maybe a unit in a strip mall almost. You know, it's pretty small. And so I'm sure you have a standalone controller. You don't have a huge energy management systems with all kinds of sensors, but you do have things you can do. For example, you can make sure that system is calibrated. You can make sure that your lighting systems are the most efficient. And in fact, I don't have a lot of time to respond to this, but I could talk to you offline about energy performance contracting in small buildings where you can have folks come in, like for lighting, for example, and put that lighting in at no cost to you and pay down the cost of that installation through the energy savings, and actually they'll kick back, in some instances, 15%. You can actually get paid to have better performance in your lighting. And so my response is that everything is energy. Every type of facility, I don't care if it's your home, I don't care if it's a room, even if you get down to the smallest room, there's energy involved with it, and we can all do a better job with that.
Joe, I want to thank you today for this session and remind the listeners that there's a follow-up, part 2 of this, on May 12th. At the end, there's going to be a survey. Please complete it. And to remember, to qualify for a free copy of Dr. Jacobsen's book, all you have to do is attend each of these webinars and complete the quick survey. So again, we thank you very much for your attendance today. For those of you who couldn't stay through the whole thing or didn't start on time with us, we will be posting this to the Eagle website for those attendees.